Okay, so we're going to have a look at Chapter 9, which is Advanced Positional Tolerancing Concepts. And we're going to spend a little bit of time going through some examples and demonstrations of the concepts here. There is a PowerPoint presentation for this, but I feel like going through examples and demonstrations for this are going to be much more helpful and instructive for you to understand what's going on. Okay, so first of all, I'm also going to use figures from the book for the most part. I have one example that I want to do later that is not a figure from the book. But so first of all, with composite positional tolerancing, what we're talking about is a dual feature control frame. So we have a two-segment feature control frame. The upper feature control frame or upper segment and the lower segment here. But importantly, we have a single tolerance symbol. Okay, so so that's an important distinction and kind of signal that we're talking about composite positional tolerancing. Okay, so what does a composite positional tolerance do? Well, first of all, it does what a normal positional tolerance does, okay? And the normal part of a positional tolerance can be seen up in the upper segment here, okay? So this diameter O35 tolerance zone at maximum material condition relative to datums A, B, and C, that's just your regular positional tolerance. This upper segment is what's called the pattern locating tolerance zone. Okay, it is sometimes referred to as PLATZ, P-L-T-Z, the PLATZ. Okay, the lower segment does something slightly different. Okay, it's the same idea, it's the same positional tolerance idea, but the important thing is how it's referenced. Okay, so you'll notice that here we only have one repeated datum reference. So here, primary A, secondary B, tertiary C. Here we only repeat the primary datum A. All right, this is called the feature locating tolerance zone. Okay, also abbreviated FLATZ, F-L-T-Z. So the upper is called PLATZ, the lower is FLATZ. In case you want to, sometimes it's a mouthful to say pattern locating tolerance zone and feature locating tolerance zone. Okay, but let's talk about what each one of these does. Okay, so we have an example here. This is the drawing, right? So on the drawing, we see this. We have a block, rectangular block with 4 holes in it. And we have a composite positional tolerance on these 4 holes, right? So the 4 times means that this is for all these 4 holes simultaneously. Okay, and we have a PLATZ of O35 tolerance zone at MMC relative to A, B, and C. And we can see A is the bottom surface here, B is this long side here, and C is the shorter side perpendicular to A and B. Okay, so what the pattern locating tolerance zone is, okay, the pattern locating tolerance zone is going to be a tolerance zone that is going to locate the axis of the 4 holes, right? Because that's what we're really controlling here, an axis, right? The axis of the 4 holes within a tolerance zone that is 0.035 in diameter, okay? And you can see that down here, right? So we have, and it might be a little bit hard for you to see here, but in your book, you can look at this figure in your book. We have the dotted circle right here, okay? So the dotted circle is the O35 tolerance zones, okay? Now, what's important to understand about the O35 tolerance zone, the PLATZ, the pattern locating tolerance zone, is that the pattern here, the 4 O35 tolerance zones are fixed to the datum reference frame. Okay, So that means that relative to A, they are 90, I don't have a side view here, but relative to A, the tolerance zones are a perfect 90 degrees relative to A. Relative to B, they are exactly 0.375 up from B and 1 inch from there. And from C, it's a ½ inch from that datum and 2 inches from that center mark. Okay, so these O35 tolerance zones are fixed in space at these exact coordinates. All right, and they can't move. All right, so ignoring the flats right now, ignoring the bottom segment, the upper segment, it simply says, hey, the center of these 4 holes must lie within the O35 tolerance zones, which are fixed in space exactly at 375, 1, half, 2. They're locked down in space and 90 degrees relative to A. Okay, they're locked in space. So as long as the center for these 4 holes lies within this O35 tolerance zone, then everything is good. Okay. So then where does the flats come in? The feature locating tolerance zones. All right. Well, the feature locating tolerance zones, in this case, reference to A only, reference to the primary datum only. The feature locating tolerance zones are free. The tolerance zone itself are free to move within the O35 tolerance zones, provided that the feature locating basic dimensions are maintained. Okay, so this includes, because we have a repeated primary datum, this includes the tolerance zones must be 90 degrees relative to A. But other than that, notice that it's a little bit hard to see here, but notice that they are not constrained to B and they're not constrained to C. So these 4 tolerance zones, the O15 tolerance zones, are free to move and shift, provided that they stay 2 inches apart and 1 inch apart here, okay, and 90 degrees relative to A because we are repeating this datum. All right, and that's the feature locating tolerance zones. Now, you might be wondering why we would want to do this, okay? And before we do that, let me just back up just a second and add something here. You'll note, this is important, you'll notice that the tolerance zones for the plats, the pattern locating tolerance zones, is larger than the flats. And that's something that must be the case, okay? You can't have the flats larger. It always has to be the plats, the pattern locating tolerance zone, tolerance is larger than the feature locating tolerance, okay? O35 is larger than O15. Everything else has to repeat in here. So if it's maximum material condition here, this has to be maximum material condition. All right, and it has to be the same datums. However, you get to choose whether it's 0 datums, 1 datum, or 2 datums. All right, you can never repeat the 3rd datum, but it's 0, 1, or 2. And we'll talk about the differences between 0, 1, and 2 in a second. But let's talk about why this is the case. Why would we want to do this, okay, with the pattern and the feature locating tolerance zone? And let me bring in a little example here, okay? So let's say that we have a wall, right? This is a wall in our house. All right, and let's say that we want to attach this outlet cover to the wall in the house. Now, what's important about making sure that we can attach this outlet cover properly? Okay, so what's super important is that the holes here, where the screws are going to affix it to the wall, that these holes are pretty closely spaced to where they are in the outlet cover. Okay. In other words, I can't mess this up and put one hole here and another hole way out here, because then I'm never going to get the outlet cover in. So the tolerance zone for the 6 screw holes here, the tolerance zone for the screw holes needs to be pretty tight. Okay. So if I was going to, if I was going to make a drawing of this outlet cover and assign a positional tolerance to these 4 holes, I would need to make sure that the tolerance zone for these, 6 holes, for these 6 holes is relatively small, because I can't have a lot of deviation here. I can have a little deviation, but I can't have one hole here, right? And another hole way out here, or another hole way down here, because then I'm never going to get it on. So the tolerance zone, the acceptable tolerance zone for these 6 holes has to be pretty small. But is that real? Is that the same tolerance zone for how I want the orientation of the holes relative to the side and top of the walls? Well, no. Does it really matter if the outlet cover is here, or maybe here? I angled it a little bit, or maybe here, or maybe here. All right. If we go around our house, you're probably going to find that the outlet cover is not in the exact distance from here and here in every wall, right? It could be a little bit like, well, maybe not that bad, but you know what I mean. It can be a little bit off. It can be a little bit off here. It can be a little bit higher. It could be a little bit closer, a little bit farther away. So we have a larger tolerance zone for the pattern relative to the, in this case, the edges of the wall. That right there is why we have our pattern locating tolerance zone and our feature locating tolerance zone with different tolerances. So the feature locating tolerance zone is the tolerance zone for these holes, and I'll mark it right here. All right. I don't know if you can see that, but I'll make these a little bit darker. This would be the tolerance zone for the features, right? The 6 holes are the features. But the pattern itself, as long as I keep these features this far apart and this far apart, does it really matter if the features are up here right there? No, not really, right? We don't want to throw out our whole wall, so to speak, because we drilled the holes here, as long as this distance x is the same as this distance x. And as long as this distance y is the same as this distance y. Okay? So that's where the pattern locating tolerance zones and feature locating tolerance zones, let me bring this back in, come into play. Okay? The pattern locating tolerance zone just says that, you know, the 4 holes can be in a larger pattern, provided that they are appropriately located from the datum reference frame, A, B, and C. Okay? The feature locating tolerance zone says we're not going to worry about their location relative to, in this case, B and C, but we want to still ensure that they are located relative to each other. So the 2 and the 1, in this case, the 2 and the 1, and you can see that here, the 2 and the 1. See how this is an angle with the blue lines? Okay, so this right here, this is the pattern locating tolerance zone. This right here is the feature locating tolerance zone. This right here is the feature locating tolerance zone. And here we have the pattern locating tolerance zone. Okay, so that's where this whole concept of composite positional tolerances comes into play. We don't want to reject something, right? We don't want to reject a part because the holes are too close or too far away from the sides, when that really doesn't matter. What matters is the location of the holes relative to each other. And that's what the feature locating tolerance zone says. Okay. Now, let's look at another example here. Now we'll look at the difference between the repeated datums in the flats. Okay, so in this example here, you can see that, right, in this example here, you can see we have no repeated datum references. Okay, so we have these three holes. We have a pattern locating tolerance zone of O25 at MMC relative to A, B, and C. And so here's A, B, and C is right here. So B is the long side, A here. And so the tolerance zone here, if we look down on the example here, right, this is the drawing. So the tolerance zone here, we can see the dotted line right here, the dotted circle right here. The dotted circle is fixed in space, 0.531 from datum B, 450 from datum C, and again, there's no side view here, but 90 degrees, actually we can see it down here, 90 degrees relative to A. Okay, so that's the larger one. Now, because we have no repeated datums here, then what that means is the flats, the feature locating tolerance zone, is unconstrained and free to rotate and translate within the pattern locating tolerance zone. Okay, so this O12 at MMC, 0.012 tolerance zone at MMC, which is the smaller tolerance zone right in there, okay, it can move. It can rotate like this. Here, you know what? Let me show you with this. Okay. So here it's right on 531. Okay. Now, the feature locating tolerance zones are free to move like this or like this, right? That's relative to datum B. That's rotation relative to datum B, right? Remember, here's datum B. So if we rotate it relative to datum B, that's here and here. So the O12 tolerance zones are free to rotate relative to datum B, provided what? Provided that they stay that they stay within the O25 tolerance zone, and that they stay 1.25 apart and 2.5 apart. So they can't move like this. And they can't, shift out. The tolerance zones, we're talking about the tolerance zones. The tolerance zones are free to rotate, all right? Because we have no repeated datums. How else are they free to rotate? Well, they're also free to rotate relative to C. Well, this is also relative to C, right? This is relative to B and C. And they're able to rotate relative to A. So that means that here, and I'll use this, that means that if this is 90 degrees relative to A, they're free to move at an angle. So they are unconstrained. The feature locating tolerance zones, the 0.012, is unconstrained relative to the datum references. All right. What's important here is that does not mean that we forget about these basic dimensions. All right. All right. Remember, the feature locating tolerance zone never includes the locating basic dimensions relative to the A, B, and C, but only the feature locating basic dimensions. In this case, 125 and 250. 125 and 250. Okay, so that's 0 repeated datums. Let's look at 1 repeated datum. All right, so we have one, same figure, same drawing. We have 1 repeated datum. All right. So, and notice that we always repeat the primary datum first and then the secondary. You can't skip it and do do B here. It has to be A. All right. So now, because we're repeating A, that requires that the feature locating tolerance zone is constrained in its orientation to the primary datum. What is the primary datum? The primary datum is A. So that means that, and let me get my little aid here, that means that the the tolerance zone here, the feature locating tolerance zone, must be oriented 90 degrees to A. So in the previous example, we could have a tolerance zone that is an angle relative to A because we had no repeated datums. Now we repeat the primary datum. The primary datum is this bottom surface. So the tolerance zone, the O12 tolerance zones, must be 90 degrees relative to A. All right. Now, because we don't repeat B and C, the tolerance zones are still able to be oriented relative to B and C. Okay. So that's a single repeated datum. Now, the most repeated datums that we can have with a composite positional tolerance is 2. All right. So here's an example. Whoops. I guess I do not have 2, but we can make do with this. So a second repeated datum would look like this. Let's put that in there. And what would that do? So now we have 2 repeated datums. Well, it requires that it first is oriented relative to the primary. So that means that the tolerance zone, the feature locating tolerance zones, O12, must be 90 degrees relative to A. 90 degrees relative to A. Okay? But because we repeat B, then the tolerance zones must be oriented relative to B. So that means that in addition to 90 degrees relative to A, here's the axis connecting all the feature locating tolerance zones. This axis cannot rotate like this. Relative to B, it must remain parallel to B. Remember, this is B right here. So the tolerance zone the tolerance zones must move so that they maintain their parallelism to B, right? So they can be up here, they can be down here a little bit, whatever. They cannot twist like this, okay? So that's when we repeat B, the secondary datum. Now, you cannot have a tertiary datum repeated in here, okay? So that's not allowed because then it would just be fixed in space. They would not move, right? And so this would become the only datum that matters. This one wouldn't really matter much, okay? All right, so that's repeating 0, 1, and 2 datum references, okay? Now, we're going to Okay, so let's look at an example now, putting these concepts of composite positional tolerance together. So what I have here is my design for a box, and the box is going to have this cover plate attached to it. Okay, so we're designing the box, right? And this is the drawing of the box right here, and you can see I have the 6 holes that are going to be used to fix the cover plate onto the box. All right. Now, I'm the designer, so I know what I need and what I'm looking for here. And what is absolutely critical with this, with the box that I'm designing, is that the position of the 6 holes are as precise as I can get it, right? I can't have one hole here and another hole way down here, or else it's not going to work. Okay, so the position of the holes relative to each other, the features relative to each other, has to be relatively tight. All right. Now, what I can be looser on is the holes relative to the sides here, right? So as long as I maintain the orientation of the 6 holes relative to each other, it's not a big deal in my design whether all 6 holes are a little bit closer to the right or a little bit closer to the top or even a little bit at an angle, right? That's not important. In order for the cover plate to still function as a cover plate, the holes must line up relative to each other, but it's not so critical their position relative to the sides, okay? So that's a perfect situation for composite positional tolerance. All right. Now, let's go ahead and figure our datum reference frame. All right. So the datum reference frame for this, the primary datum is going to be the top surface here, the surface of the box, because I want the cover plate to attach flat. All right. So I'm going to make this is my primary datum A. And then I'm going to make my long edge, because it's a long edge and it's going to be a little bit more stable. I'm going to make that my secondary datum B. And then my shorter edge out here, almost running out of room, I'm going to make C. So my datum reference frame for this, for these holes, right, is going to be A primary, B secondary, and C tertiary. So that's where this part lives in the assembly. Okay, A, B, C. Now, let's work on the tolerancing for the holes, all right? So these 6 holes are going to be tapped, right? Because I'm going to have a screw that's going to go through here. This is a clearance hole. The screws go through the clearance hole. And in fact, you can see there's a slight countersink. So these are going to be flathead screws. Flathead screws are going to go through here, and they're going to thread into these holes. So these are 6 tapped holes, all right? So I will go like this. Now I've already measured these, and these are a diameter 4. Let's not worry about the countersink. So these are a diameter 4. So the tap here is going to be an M4. Whoops, and I got to put in, can't forget the 6 times, M4 by 0.7. That's the size of the tap that's going to go in there, size of the thread that's going to go in there. So I have 6 M4 by 0.7, that's the pitch, holes that are going through here. All right, now let's figure out the tolerance here. Okay, so we can start, we're going to use a composite positional tolerance, right? But how are we going to start with this? All right. Well, we're going to start, this is a perfect example of a fixed fastener case. All right, so what are the things that we know? We know that the fastener is an M4, right? So that means it's 4 millimeters in diameter, and that is its MMC size. Okay. I know that these holes right here are going to be a 4.2 to 4.6 diameter. That's the tolerance range on those on these holes. All right. Not these holes. These holes are M4. The holes in the cover plate are 4.2 to 4.6. So the MMC size is going to be that minimum hole, 4.2. So the fixed fastener equation is T equals H minus F divided by 2. H is 4.2. F is 4 divided by 2 equals 0.1, right? 4.2 minus 4 is 0.2 divided by 2 is 0.1. So that is my tolerance on these 6 holes. Now, which tolerance is that, right? Is it the pattern locating tolerance zone or the feature locating tolerance zone? Well, this is this is the most restrictive tolerance, and the tightest tolerance must go on the flats. So this is 0.1. We're going to use MMC because we have a clearance condition, not in the tap necessarily, but in the other one. All right. And let's leave off the tolerances right there. So, excuse me. So now I have my pattern locating tolerance zone. And here, there's not an equation for this. This is just where we get to say how tight or how restrictive we need this to be. And I'm going to say, since the holes are going to be 0.1 tolerance zone, I need to be more than that. Obviously, remember the pattern locating tolerance zone is more than that one. It has to be more than that one. So I'm going to say that this can be, a 0.5 millimeter. Right? That's pretty good. The tolerance of 0.5 at MMC. All right. And now relative to what? This one is A, B, and C. That's our datum reference frame, A, B, C. So how many repeated datums do we need here? Or do we need any? Well, let's ask ourselves. All right. So in the application of this cover plate, might be a little bit hard for you to see here. Let me do that right there. Okay. So if the holes are not perpendicular, then I have problems with the screws going in, right? If the holes are not perpendicular, then maybe I have the cover plate kind of cockeyed. Maybe I can't even get the fastener through there. So I want the holes to be perpendicular to A. Other than that, can I tolerate the cover plate being slightly at an angle? All right, so we need A there because we want the fasteners to be perpendicular to A. Can I tolerate the cover plate being at a slight angle? If yes, then that's it. If I want the cover plate to not be at an angle, so in other words, it can be a 0.5 millimeter up and down, left and right, but it cannot be twisted, then I need to repeat B. If I can tolerate the cover plate being slightly twisted, right, then I have only A. Now let's say for appearance sake, I don't want the cover plate to be twisted. So I'm going to repeat B right here. So I'm requiring that the tolerance zone 0.1 at MMC be oriented relative to A, as in 90 degrees, and be oriented relative to B. That means B is this one. That means that it must be parallel to B. It can move like this. It cannot move like this. Okay? All right. And so there we go. All right. Now let's finish this up. All right. Now I'm going to use different color pens here so that it's a little bit more clear. So I'll use green and I'll use red for the different ones. Okay. And just so you can get these a little bit, tied in, let's do this as the green is going to be the pattern locating tolerance zone, and the datums locating the pattern locating tolerance zone framework is going to be, well, A, 90 degrees, that's understood. B, we're going to be I'm making up these numbers, by the way, so. And C all right. Now, of course, we still need to do all the holes relative to each other. So that's going to be here. And that's going to be, let's see, this, I'll put it down here. Basic dimension here. And then here, this is going to be all right. So there's our completed drawing, right? Obviously, we're leaving out a few things like the outside of the box right here. But in terms of these 6 holes, right, we have 6 holes that are M4 tapped with an M4 by 0.7 thread, okay? They're located relative to ABC with a tolerance zone of 0.5 at MMC. And A is understood to be 90 degrees, right? We don't need the dimension for that. B, they're located from B, 35 millimeters basic, okay? And from C, 50 millimeters basic. And then the feature locating tolerance zone is 0.1, calculated with our fixed fastener equation, okay? T equals H minus F, where the hole size in here is minimum 4.2, so that's the MMC size of the hole. And the fastener is an M4, so the MMC size is 4 millimeters. And that gives us a tolerance in the feature locating tolerance zone framework of 0.1 at MMC relative to A and B. All right. So that means that A and B, it needs to be oriented relative to these datums. And the feature locating tolerance zones are basic 60 millimeters apart and 45 millimeters apart this way. All right. And so that's the solution for this example of designing a box for this cover plate. Now, if we went on to design the cover plate, okay, what would change between this drawing and the cover plate drawing? Well, the 6 times we would replace the M4 by 0.7 with the hole dimension, 4.2 to 4.6. All right, so this thread note will go away, and it'll be 6 times 4.2 to 4.6 and something for the countersink, right? This right here, this composite positional tolerance would be exactly repeated for this, all right? A would become the bottom surface here because that's the mating surface for A down here, right? This side would be B, and this side would be C. This 60 and this 45 and this 45 would also be exactly repeated in the drawing of my outlet cover. Okay, and then I would have the 50 here would change to whatever this dimension is from here to here, which is actually 35 millimeters. And the 35 here would change to whatever it is here, which is in fact 28 millimeters. Okay, so that's how this would change. All right, so we could do also the cover plate here, the drawing here, but this is just the box that the cover plate is going to sit onto. All right, so in the next video, I'll do some examples of how to determine the gauging for this. All right.